This video is sponsored by CuriosityStream. Get access to my streaming video service, Nebula, when you sign up for CuriosityStream using the link in the description. Neil Armstrong describes setting foot on the moon as one small step for man, one giant leap for mankind. The National Space Society tells us that returning to the moon in a big way will accomplish 4 of the 31 critical steps toward interplanetary settlement. So today we are continuing our look at becoming an interplanetary species. In parts 1 and 2 we took a look at the first steps, getting into orbit and colonizing cislunar space and our Lagrange points, and today we'll be continuing our development as we look at getting a base on the moon and growing that into a permanent facility to serve as our stepping stone to the other planets. As before, we'll be using the National Space Society's Roadmap to Space Settlement as the loose guide, and I've linked the complete document in the episode description. The NSS considers Part 3 to be a return to the moon, and the milestones for that will be our focus today, though we will not hold to it rigidly. Also, the moon is a topic I try to hit about once a year. The principal episodes for that in order of production are Moon-Based Concepts, Industrializing the Moon, Battle for the Moon, and Moon, Crater Cities. And while we could easily do a dozen episodes just on the moon without denting the material to discuss, some parts of today's topic we've looked at before in greater depth in those episodes, so I'll mention and link those episodes as we go if you want to dive in a bit deeper. Now, last time we talked about how we needed the moon as a resource source for developing cislunar space and launching out beyond the Earth-Moon region to places like Mars and the asteroid belt, all main topics for episodes 4 and 5. However, setting up the moon as some sort of massive mine and manufactory is not something we'll do overnight and will have a lot of intermediary steps, though I suppose one could argue we've already mined the moon, as collecting rock samples was a primary mission for the Apollo project. This, however, is our first milestone in Part 3, Milestone 18, Robotic Confirmation of Lunar Resources. Sending folks to the moon is dangerous and expensive. It's frankly amazing that so few lives have been lost during space exploration, and a testament to the skill of the engineers and mission planners and operators, not to mention the sheer willpower and courage of the astronauts. We should not forget though that we lost the Apollo 1 crew and nearly lost Apollo 13. Given that we only had 12 men on the moon and lost 3 and nearly lost 3 more, that's not a ratio that encouraged us to try more manned missions, even with decades more technological development, when a robot can do a given mission easier, cheaper, and safer, and in some ways better. Before we can develop a permanent base on the moon, we need to know where the resources are, because unless launch costs drop massively, as they might, see the Upward Bound series for some of the options, then we can only do such a base with either a very meager level of resources, or by sourcing a lot of them on-site, what is called in situ, and ISRU, in situ resource utilization. Creating a rover that masses maybe 100 kilograms and has wheels, a remote, a battery and some solar panels, a spectrometer and some sample containers, and some sort of excavating apparatus is obviously well within our current capabilities, and the moon is close enough for effectively real-time remote control of the rover. It would be relatively easy, compared to a manned mission, to drop dozens or even hundreds of such drones down on the moon to collect data and poke about for things like water ice or mineral deposits. Of course, this is after we've refined and validated our designs currently in development. The low gravity on the moon, combined with the talcum powder-like surface, makes getting enough traction for digging difficult, and the larger deposits we're looking for may be below that surface, and beneath that top layer of fine, dusty regolith, lunar soil gets compacted and hard. Another thing to consider is that if we intend to set up large refining and processing centers, we need to find areas with large and varied deposits. Much of the ore extraction and refining processing is complemented by other materials and byproducts, where one type of ore may yield materials not necessarily profitable for export, but useful for processing of other ores, or useful in alloying or compounding into other materials for local use or export. The more varied the inputs, the more varied and valuable your products. But detailed, on-ground surveying of the moon isn't just for finding a few good spots for initial bases. It is easy to forget that the moon is covered in craters, and at the bottom of those craters are meteorites. Since the moon lacks all the biological, hydrological, and geological processes of Earth that remove craters, the semi-intact objects that impacted there and caused them are basically still there, If you get good enough at surveying such craters, you would be able to spot which ones were made by which kind of rocks, and might find some very valuable metals and minerals in them. For instance, carbonaceous chondrites, which are a relatively rare type of meteorite on Earth, as few make it through our atmosphere, don't contain many scarce or valuable elements on Earth, but they would be more common on the Moon, and their carbon and organic compounds, containing volatiles, amino acids, and rare light elements, would be prized. But we won't limit our exploration just to the surface. Lava tube skylights allow access to vast subsurface spaces. Lava tube spelunking probe designs are being evaluated to explore these hidden interiors. These designs consist of a rover which carries the probe to the skylight and lowers it with a tether. The probe then rappels down into the tube, then becomes a simple rover. The tether either stays attached to the probe, acting as an umbilical for power and data, or detaches and becomes an antenna for communicating with the now self-powered probe. However, we may want to go a step further, as our technology has improved a lot in robotics and does more every day. Indeed, this recent health crisis has had the silver lining of accelerating both our capability and usage of remote work, and doubtless we will be seeing major improvements in those technologies in years to come as more and more folks opt to work remotely and the tools for doing so expand. In a sense, at the timescales of space exploration projects, robotic telepresence for exploring the Moon is not that far off. Necessity is the mother of invention, and that's a thing to remember for space exploration too. There's a good chance we will encounter both problems we did not expect out there and find solutions for those, and adaptations of them useful for back at home that we just cannot see right now. But we are still in the early days, so our options are limited. However, not too limited. For instance, it is just as easy, if not easier, to make a rover that has just a scoop or dozer blade on it, as opposed to mineral surveying gear, and have one shove regolith into a heap or mound. It is also not hard to include a solar kiln that can bake oxygen out of regolith. The Moon's regolith is mostly oxygen by mass, tied up in minerals with elements like silicon, iron, calcium, and aluminum in that order. If you have a solar kiln extracting those elements, then oxygen is actually a waste product. We do want those other elements too, and as we looked at in our last episode, getting megatons of iron or aluminum off the Moon is critical to developing cislunar space, as the fuel bill for moving raw materials from the Moon to low Earth orbit is orders of magnitude cheaper than from Earth's surface, even though it means moving those resources 1,000 times further. Regardless, it is not beyond our technical capability even now to make a remote-controlled production chain that would involve rovers scooping regolith into solar kilns to produce the refined metal as bricks, sheets, rods, or thin foils. There's likely to be a lot of minor practical issues in adapting anything made on Earth to work on the Moon, but a first wave of soil and resource surveyors would probably make that adaptation much easier as we learn what works in practice and what doesn't. Now, our losses in the space programs are generally not from day-to-day operations, on space or on the Moon, but the launch and transit phases. Nonetheless, a robotic presence that had either constructed an initial habitation module or provided most of the bulky raw materials for assembly not only helps cut down on the risk to astronauts once they land, but gives us a lot more mass to add extra safety features and redundancies or thickness of shielding to the vehicles going there. In an ideal scenario, when we get to Milestone 19, our lunar research and development facility, that first outpost will already be pretty well supplied. Gravity is low on the Moon, which means you can pile a lot of regolith on top of something like a thin sheet of metal supported by some metal tubes to make essentially a large and very sturdy tent. Similarly, we can fly in some supplies and equipment before the astronauts even arrive, dropping packages of food, batteries, spare fuel or air or water, and so forth for the drones to stack into cover in such a tent. We can also have them clear and mat down a landing pad free of lunar dust, so that when the astronauts arrive, they essentially just have to get out and do some assembly of whatever was beyond the robot's abilities, and from cargo that arrived in quantity before they did. Robots will play a big role in developing the Moon, fundamentally because our key long-term interest in the place is to turn it into a mass manufacturing facility of fuel and construction material that relies heavily on automation, especially handy if we opt for using nuclear power to run things, but for now let's turn our eyes to that first manned outpost. First off, location matters. We already know the preferred spot in a general sense, and that is near the poles. The Moon has a day that is a month long, making solar power difficult, and part of why atomic power sources, both reactors and radioisotope thermal generators or RTGs, are attractive. Fortunately, near the poles this is less of an issue, as we can take advantage of various high-walled craters and the latitude to get to spots where the sun shines most of the time. Those same craters, down near their bottoms, will tend to have very cold spots which might be heavy in some valuable materials. This is why those robot surveyors will be handy, since they can poke around and find which, if any, crater is high in something like water ice. We discussed this more back in the spring in our episode Crater Cities. Of course, lava tubes are also prime candidates for lunar cities or bases, and may contain ice deposits inside their permanently shadowed interiors too, and they have inherent shielding and meteorite protection. But what sort of research are we going to do there in this first outpost? One of the most tempting is radio astronomy. There is no dark side of the moon in the sense of sunless eternal night, except down in some of those crater bottoms, but there is a side that is dark to the Earth, and all of Earth's noise. There are also other science projects or lunar development projects better done in spots not on the poles, and we also have a lot of interest in the moon's enormous lava tubes. So while that first base is likely to be mostly about R&D for using and colonizing the moon, it strikes me as very likely that it would not develop further as a science outpost so much as a support hub for many smaller outposts. As an example, if we have air and metal production being done at one site, it's very easy to bring that air into some smaller facility of researchers who just have a cache of supplies and a modest amount of solar panels and RTGs to power the place. Atomic power sources are very attractive on the moon, incidentally. There is uranium there, plus uranium is also very light in terms of its energy density compared to chemical fuels, if you need to bring it in from Earth. And you don't really need to worry about meltdowns wrecking an area. The moon is already a radiation-scoured desert. Such being the case, it is a great place to be setting up breeder reactors like those we discussed in the Future of Fusion a couple weeks back. It's a very attractive place to do nuclear research, and what's more, producing plutonium-238, which emits about 500 watts per kilogram and has a half-life of 88 years, is a potential boom market for a lot of space enterprises, since it offers a reliable and small power supply. Ditto strontium-90, which is easier to produce and has about the same power density, but is shorter-lived and needs more shielding. Shielding is obviously not an issue for stationary objects on the moon, but adds extra mass to moving vehicles and spacecraft. Regardless, that first research outpost is likely to be mostly about researching the moon and how to exist there. Satellite and smaller outposts focused on various research projects may pop up, but that place is the one likely to be where we are shipping stuff to and trying out ideas like lunar hydroponics and domes, or extracting water and metals, or synthesizing fuels. And from this, we would expect our first continuously occupied multi-purpose lunar base to coalesce, Milestone 20. Its non-commercial applications of R&D aside, we can expect to see some commercial uses popping up. As an example, if we place it near a source of volatiles, things like nitrogen, water, carbon dioxide, and so forth, that we think we might find in some of those craters for instance, then we have a source of organic elements for use not only on the moon, but on those cislunar space stations and habitats we discussed last time, rather than having to get them off of Earth, or bring them in from beyond the frost line from the asteroid belt or moons of gas giants. There are some hurdles to this, of course. We do not know if those volatiles exist on the moon yet, and that's why we need those robot surveyors. I also mentioned earlier that it would be nice if our robot could pre-build a base, and mentioned having them make a nice clean launch pad for ships to land on. And moon dust is a real worry. The dust is sticky and abrasive and drove our astronauts to distraction. It can damage equipment, and given how sharp the particles are, may be very bad to be breathing or touching for extended periods, and is often considered one of the biggest hurdles and headaches of lunar exploration and development. On the upside, the moon is basically a big sandbox, so it's easy to maneuver the stuff to form shielding against radiation and meteors, and due to the low gravity it doesn't require a lot of structure to hold up even meters-thick shielding. The dust is part of the reason why solar power isn't considered the greatest solution on the moon. Besides getting dark for a couple weeks at a time, your solar panels or mirrors might get coated in dust in short order, stirred up by your own activity, and while you could have a robot or person go out and sweep them and polish them when they get scratched, it is another reason why nuclear is fairly attractive on the moon. We also talked about some other approaches to solar power like thermal waddies in the Crater City episode. Another problem with this multi-purpose approach is also its big advantage. Having many different functions gives it some diversity for funding and operation, but also could cause funding and turf conflicts between various divergent space goals and the government branches or companies funding or operating them. This is probably even more the case if it's a multi-government international project, And interestingly, I would not be surprised if the first moon base was actually a commercial enterprise that various governments, companies, or institutions rented facilities and time at. One silver lining of bureaucratic battles over space and funding is they might also encourage separate satellite facilities to form too. We discuss such issues more in Battle for the Moon. It should also be noted that just because the poles and craters interest us, we don't necessarily put our first base inside one. If your main interest in them is the rim walls for solar power and the crater bottoms for volatiles, you might just opt to go mostly nuclear instead of dragging solar panels from home and operating them around the space dust issue, and just sending out rovers and collection teams, human or robotic, to collect volatiles and bring them home. After all, Aristarchus Crater and Plateau in the northwest of the moon's near side is also considered a very attractive site for its geological or semiological features and may reveal more about the moon itself and the treasures it may offer than other locations. In any event, after the space has been in continuous use for a decade or so, and hopefully grown and prospered there, this is where we come to finally having reached milestone 21, a permanent lunar settlement. Here we might see people actually living on the moon, maybe even born there, and we have to start tackling issues like building schools and community spaces. You get your first hospital on the moon, your first daycare center, first park or garden, first lunar hotel, first bar, first restaurant, the first church of the moon, the first low-gravity basketball court, and so on. For that to be practical, we need to be able to get most resources, at least by weight, right there on the moon, but that's a double necessity anyway, since all those things imply jobs and livelihoods beyond simple resource installations, and resource production for cislunar space, as we looked at last time, is essentially what is likely to drive lunar development. After you have gotten all the science done there, which admittedly could be an ongoing project of thousands of researchers for centuries, you have to have a reason for development, and that is as a supply hub. The mass extraction and fabrication of solar panels, shades, and mirrors may be one industrial focus. Another might be fuel production for moving around cislunar space and station keeping. Another might be huge amounts of metal plates for building space stations and habitats. Exporting volatiles is another, but would depend a lot on the supply and availability of them, and we really don't know yet. That's one hurdle we still need to overcome. Same, we don't really know if they're all good concentrations of ores. We know we'll have no shortage of aluminum and iron and silicon, of course, but not necessarily other useful metals in a way that will be easier than getting them off Earth, for all the launch cost issues, or from the asteroid belt a bit down the road. And by the time we have staged up to this level of production and occupation, we probably have gone on to both the asteroid belt and Mars. We also don't know how humans will handle living on the moon. There is gravity there, and it may be enough to stay healthy without significant treatment, but there are many medical and psychological unknowns still. It is possible people won't handle living on the moon for extended periods very well, and we might have to have more frequent personnel rotations, or go a lot more robotic, which might hamper many projects. Once you have this first big permanent base though, or while you're building it, hopefully you will have picked the ideal power source for the moon, got it going big, and be running all that production. That might include fuel of course, even if it is short on volatiles, aluminum and oxygen can't be used as a rocket fuel, and you might also build a mass driver or electromagnetic coil gun for launching things into space. The escape velocity from the moon is just over 2 kilometers a second. There's no air for friction there, so a catapult doesn't need its payload to ascend above the atmosphere like it would on Earth, since there ain't one, so it might be the preferred way of shooting stuff into cislunar space. Or onto Mars and the asteroid belt, our next 2 episodes, and as we'll see there, the ability to robotically explore those places and pre-deliver large amounts of goods before humans arrive, potentially launched from the moon and for some of it manufactured on the moon too, could be a massive boon. Getting to Mars will be no easy thing, but in truth, if you have a solid base and production set up on the moon, with or without the accompanying cislunar development, that task becomes an order of magnitude easier, while at the same time you've already solved a lot of the problems a trip to Mars will include. There's always some debate if we should go to Mars first or back to the moon again. Like most of you, I would be happy either way, and I do believe it is possible to go to Mars without this stop at the moon, but it strikes me as far harder and more risky. The moon is close enough for real-time conversation with Earth, and only a few days away by conventional rockets if we need to get them help or evacuate. We would hopefully be able to rescue people from the other bases on the moon, but if it came down to it, a lone astronaut with a spare air tank could potentially survive for the few days needed to scramble a rescue mission right from Earth orbital facilities if need be, while experts at home can devise real time on what they should do to survive. This won't be an option for Mars, so it is best to work out a lot of the kinks on the moon before trying our hand there. Those same long travel times and hardships also encourage us to want to start from day one on Mars with a permanent base, not a small expedition to land, plant a flag, and get some rock samples. As we'll see next time, setting up a base on Mars will be no easy task. So this was the third episode of the series, and we bumped it up earlier in our schedule because of demand from the audience not to wait. If you didn't know though, it actually came out a few days earlier over on Nebula, our new streaming service, and all of our episodes come out there now a bit early and ad-free. If you'd like to catch all of SFIA's episodes early and without ads, or see any of the great content from our sister channels on Nebula, you can sign up for Nebula today. However, you can also get it for free by instead signing up for CuriosityStream, who's partnering with us to bring you the best education videos out there. CuriosityStream has excellent educational content of their own, and they are running a 26% discount if you use the link in the description. That's a great deal since it means you get a year of both CuriosityStream and Nebula for less than $15, and helps support this show and a lot of other educational content, which is what CuriosityStream and Nebula are all about. And again, you can get a year of both for less than $15 by using a link in the episode description. So as we mentioned, we are continuing our look at becoming an interplanetary species, and in 3 weeks that will take us to Mars and our first colony there. Next week though will be a bit closer to home as we contemplate the notion of megacities, the popular and often dystopian concept in science fiction, and we'll look at the challenges and interesting scenarios for cities on the go. Then on Sunday, October 11th, we'll be taking a look at the recent Navy UFO videos and analyzing those. And in 2 weeks we'll be contemplating the notion of a low-tech spacefaring culture. If you want alerts when those and other episodes come out, make sure to subscribe to the channel. And if you'd like to help support future episodes, you can donate to us on Patreon or our website, isaacarthur.net, which are linked in the episode description below, along with all of our various social media forums, where you can get updates and chat with others about the concepts in the episode and many other futuristic ideas. Until next time, thanks for watching, and have a great week.